think I'm just going to dive right in. I thought I would, I'm going to start just with a brief visual of the project local code that Jeff was discussing. This is several hundred models that we made, proposals for parcels in San Francisco that I'll be presenting later on this evening at an event at Cooper Union as part of the groundwork exhibit, groundwork book recently published by Monchaux with Joel Sanders and Dan Belmore being the collaborators on the book. So that's my little plug for them, which I promised them I would do. And we'll get straight into spacesuits. But can you guys see that image okay? No?
Put some more, thanks.
Yeah. So what you'll see in a second is that this image is one of, that's in the book, of John F. Kennedy wearing a spacesuit. And the interesting thing about Kennedy is that he was a master of his own public image. He would, in fact, on the theme of publicity and fashion, which is essential in this larger discussion of style and science fiction, John F. Kennedy would change his shirt up to 5 times a day, or change his shirt up to 7 times a day, rather, and change his clothes from his skin to the outside of his body up to 7 times a day, all as part of his own mastery of his own image. He was, in fact, a very sick man. He had particles of capsules of adrenaline implanted under his skin every 3 months in order to stay alive. He had a whole legion of ailments, but he hid this all enormously successfully from the world, and as a result had a kind of quintessential, I argue in the book, understanding of this vast distance that separates image from reality. When Yuri Gagarin was launched, bringing the fantastic into the realm of the real in the early 1960s, in 1961 it was Kennedy who conceived of the image of an American on the moon as, in many ways, quite literally, the ultimate weapon in the Cold War. This mediated spectacle, science fiction spectacle that was the American Apollo, Mercury, Gemini, and Apollo programs. And these programs were not, as they are often kind of understood in this vague haze of historical understanding, they weren't sort of sequential or slow, steady innovation. They were a crash program to produce this single particular image of an American on the moon. Lyndon Johnson, who studied the idea's feasibility for Kennedy, had as part of his advisors to the conception of the Apollo decision, not only Jerome Wiesner, who was the president's science advisor, but also Frank Stanton, the president of CBS. So this image of suited Kennedy, which we see again here in the Herblock cartoon, should really give to mind the notion that this was purely, almost totally, a vast billion-dollar enterprise which took a nickel out of every tax dollar in 1966 for the production of a single designed image of an American on the surface of the moon. So I hope I brought us already from a realm of government policy, space programs, these very weighty things, into what I believe is the much more appropriate context to talk about the space race and the image of the suited astronaut in particular, which is a realm familiar to us as architects, as Jeff already referenced, which is one of image creation, image production, and the design not only of objects, but also of narratives and of storylines. It was a story of the space race that also had an enormous life in the architectural media itself. And that's what I'm going to talk about mostly here today, which is whether and how this amazing narrative of sending a human being 250,000 miles to the surface of the moon and back and recording it for posterity, how this had a life in design, how we as designers might use it as Jeff was referencing in the introduction, the many different ways that this kind of narrative could become a model for thinking about how we operate in the design world. And what's interesting is if you look at the history of the life of the space program in design culture, it shouldn't be surprising to us that it had an immediate in its own time in the design culture of the day. This is the February 1967 cover of Architectural Design, which was entirely given over to a discussion of the role of the creative inspiration of the space program in design culture, full of projects by Archigram and so forth. It was edited by John McHale, who was a kind of disciple and apostle of Buckminster Fuller in London. And this is a kind of version of the space program in design that is also in some ways vaguely familiar to us. It inspired projects like Mike Webb's Crucicle or Coop Himmelblau's portable pneumatic environments, these kind of space-age portable habitats of which the spacesuit itself was kind of the sine qua non. What's interesting, if you look at the American architectural press at the time, is that you don't see a single spacesuit or a single visual component of the space program at all. Instead, and this is, I think, particularly interesting at this present moment of architectural history, instead what you see is an interest in this, which may not seem like architecture, but let me explain to you who these people are and what they're doing means. On the left is Bernard Schreiber, who was interestingly originally trained as an architect, but later became during the Depression, when there was no architectural work, he entered the Air Force. And later, what's important to the story of the space program, and indeed the military-industrial complex at large, is that by 1954, Bernard Schreiber was the commander of something called the Western Development Division, which was the part of the Air Force charged with the creation of ICBMs. There, in a converted schoolhouse on the grounds of LAX, his chief colleagues were these two guys, Dean Wooldridge and Simon Ramo, who would later found what would become the defense consultancy TRW. And the method that they devised together, which they termed systems engineering, was itself the underlying language of the space race and of the military-industrial complex at large. And it was this approach of systems engineering, which is a method devised by Wooldridge, Schreiber, and Ramo to deal with the complexity of missiles and the complexity of this design process, that proved so captivating to American architects that it excluded all discussion of the visual iconography of the space race for something quite different. And maybe I should stop a little bit and just explain what precisely systems engineering was. The Atlas missile, as with the space shuttle in its own time, was, at the time that it was created, America's first ICBM, the most complicated object that had ever been assembled by human beings. It had more parts, doing more different kinds of things than had ever been the case before. And when it was first assembled under the leadership of the defense consultant Convair, they had the problem that the missile looked great. It was shiny, aluminum, tall, like a big, powerful weapon should be, but it had the problem of exploding every single time it launched. Not for the same reason, but in fact for a different reason every time. In one prototype, the speed of the turbo pump that delivered fuel to the rocket engine was the same as the frequency of resonance of the gyroscope in the top when they interfered with each other. There were all these unexpected relationships that happened throughout the whole mechanism that led to the failure of this complicated, fragile object. So the process of systems engineering developed by Ramo, Wooldridge, and Schreiber was a process in which each individual component was conceived of as a black box. This is where the phrase black box comes from, and connected by certain parameters of performance. So the whole object could be modularized into little subsystems, and all their relationships with each other codified, made parametric in today's parlance, so that the whole object could be designed, each part, and brought together and make a functioning missile. having been conceived in the context of designing ICBM, systems engineering became the lingua franca of the space race in general, in which repurposed ICBMs were used to launch American astronauts into space, and of the military-industrial complex at large. It was a method that seemed so successful in its in the context of NASA and in the context of the achievements that it brought about, that it led Hubert Humphrey to say in this speech at the opening of the Department of Housing and Urban Development in 1968 that, quote, the same techniques that put a man on the moon are going to solve the problems of American cities. And I draw your attention to the language here, because he's not saying, as we say now, if we can put a man on the moon, we can do this, or if we can put a man on the moon, why doesn't my iPhone work downtown? Or this kind of, relationship of technological complexity. What he was saying was something very different, which is that the same techniques, the very same, by which he meant systems engineering, that put that mastered the seemingly enormously complicated, difficult task of sending a man 250,000 miles from the Earth and bringing him back, were going to solve the problems of urban America. Humphrey was speaking in the lineage of a series of reports and collaborations between NASA and HUD and the institutions that preceded it that had gone on as early as 1962. The first meeting actually took place in my hometown of Oakland. The next meeting took place in Woods Hole in 1966 and produced this report called Science and the City. The report has a great quote, something along the lines of, cities are more complicated than rockets, but they have the same qualities. That is to say, of complex connections and discernible parts. And no doubt creating a city is more difficult than creating a functioning rocket, but the same techniques will basically allow us to do one and the other. This was only one of these kinds of connections, though, between NASA and the world of HUD, these reports and meetings. Another one is represented by this image. This is, and here's my nod to Jeff's theme of science fiction. This was actually a spaceship designed at NASA by a guy named Howard Finger. And if it looks slightly familiar, it's because it was actually used by Kubrick as the model for the spaceship Discovery in 2001, a deep space nuclear-powered spaceship. Howard Finger was the director of nuclear propulsion research for NASA. He was responsible, amongst other things, for putting a nuclear reactor in a Convair bomber and flying it above New York in a top-secret mission in the 1950s to study nuclear propulsion of aircraft. So sci-fi and reality. And then he designed his deep space nuclear-powered ship for NASA. Now, there was yet another reason for the transfer of NASA intelligence to HUD, which was the massive depopulation and defunding of NASA after the giant funding peak of Apollo itself. And so this, in many ways, was responsible for two transitions of this image. The first transition was the fact that actually Stanley Kubrick, when he was doing putting together 2001 in the from 1966 to 1968, managed to, for a song, scoop up all these NASA engineers who were out of a job to work on the sets and props and costumes for 2001. So they were all actually designed by ex-NASA figures. A guy named Fred Orway, who I got to interview for the book, had the hilarious distinction of being, having served both as chief assistant to Stanley Kubrick during the filming of 2001 and of chief assistant to Wernher von Braun at the Monchaux Space Flight Center during most of the 1940s and 1950s. And I couldn't get him to say which one of those was more difficult to work for, but apparently they were both slightly problematic. So anyway, so that's one transfer of technology, was the way in which this spaceship went to become part of 2001. But the other transfer was directly to, again, the ideas of how we think about architecture in the city. Howard Finger, the designer of that spaceship, was by 1969 director of research and development for HUD. Responsible for a vast program called Operation Breakthrough, which sought to apply techniques from aerospace to problems for American cities. And people like Peter Kamnitzer, who was at UCLA at the time, produced images like this. This was the first ever architectural rendering done to study a modernist proposal for highway redevelopment in Los Angeles. And it was done using the Apollo lunar landing simulator, which was the only computer in the world at the time that could display three-dimensional virtual images. It could display up to 256 edges. To come back to this notion of the human body in space and the astronaut, when the NASA was first putting together a proposal for how mankind should go to the moon and exist on the moon, the principles of systems engineering were immediately translated to the human body itself. And this new word called cyborg, was invented by these two fellows, a guy named Manfred Kleins and Nathan Klein, who are at the Rockland State Hospital just up the river here in Orange County. They were actually a psychiatrist, psychopharmacologist, and a cybernetic computer scientist who had been part of a team at the Rockland State Hospital that had invented the first antidepressant and the first antipsychotic drug used in the United States, and therefore had this notion that the human body, after having solved these seemingly intractable psychological problems, could be made susceptible to the same principles of cybernetic manipulation and systems engineering as, say, a missile. And so their proposal to NASA, which was studied extensively, was that instead of what was called a constricting pressure suit, the human body would be like have its own system diagram laid out, and the components, like the heart or the lungs that were not capable of operating in a lunar environment, would be switched out with new mechanisms and new pharmacological prosthetics. Similarly, when the cyber proposal did not make it beyond the prototype stage, but the prototype suits that were made mostly by military industrial contractors are the ones that have mostly sustained the interests of designers and architects. This Ames X3 suit, Michael Sorkin called one of the most beautiful design objects ever made. It was clearly also the model for some of Harry Lang's designs for the 2001 suits. And it was this method of systems engineering was most finally and most grandiosely used to fuel this proposal, which was done by NASA's Ames Research Center for a 10,000-person space station to be placed between the Earth and the Moon at the Lagrange point, which is a kind of point of gravitational equilibrium. And again, you can see the von Braun's space station research, which found its way into 2001, here being re-brought into NASA, and the housing proposals of that program, Operation Breakthrough, were never actually, very few of them were actually built, and they were cited by the General Accounting Office as for being kind of ineffective and not having any impact on the housing industry on Earth. But they were utilized here in space, in this perfect utopia, as the kind of imagined suburban landscape of the space station. The space station would house 10,000 people from, I think the quote was, Western industrialized nations governed by principles from government and industry. So this kind of utopian, otherworldly, systems engineered environment has a lot to do with the kind of, I believe visually, with the sort of dystopias of the avant-garde architectural scene of the late 60s and 1970s. This perfect system-designed landscape extending infinitely, but being quite hostile in its own way to human occupation. And this brings me to the kind of crux or shift in the talk, which is that the truth of how the human body enters space, and the truth of how the human body accommodated itself to this systems engineered environment was much different than the kind of utopian imagining. And truth is always, in its own way, stranger than fiction. The actual spacesuit that walked on the surface of the moon, the Apollo A7L, was designed not by, as Jeff said, a military industrial contractor, but rather this complex assembly was a complex assembly of 21 different layers of fabric, each with a different function, all assembled together in this kind of dog's breakfast of different pulleys and ruffles and so forth. And it was designed and made not by the men of the military-industrial complex, but by the Playtex Bra and Girdle Company, which had become famous in the 40s and early 1950s for its quote-unquote living girdle made of latex, which apparently did replace even less comfortable corsets and girdles that were made of fabric and Bakelite stays. And most interestingly, it was not manufactured by men in a kind of a machine shop or systems engineering environment, but the A7L was manufactured by women who were taken directly from the bra and girdle assembly line of Playtex to the shop floor of the industrial subsidiary in Dover, Delaware, and they manufactured the spacesuit only using standard Singer sewing machines. They sewed to within a 64th of an inch tolerance, and that tolerance only existed on one side of the seam. And they sewed also without the use of any pins or fasteners in the sewing process. So it was a tremendous kind of traditional craft structure. Now, of course, for Playtex to succeed in this quest to make the Apollo spacesuit, other possibilities needed to fail, and in the end actually failed quite spectacularly. You can imagine the kind of the sort of antithesis of a generous welcome that Playtex was given when it kind of went into the military-industrial RFP for the original spacesuit proposal. The Playtex, in fact, the ILC proposal was only accepted in 1962 when NASA first put out the RFP for the Apollo spacesuit because it was so much better by a factor of about 200% than any other proposal in terms of its mobility, in terms of its comfort, in terms of everything else. But the culture of ILC, or which was known by its brand name of Playtex, was so different from NASA. The chief engineer for this project for NASA, a guy named, for ILC rather, a guy named Len Shepard, his only qualification was that he'd been the television repairman of the company's CEO and founder, and impressed him so much by his kind of crafty abilities that he was given what ended up being the top job. His chief lieutenant, a guy named George Durney, got his job in the suit making process because he was a Singer sewing machine salesperson. And he really understood how the machines worked and what they could do. But this was enormously antithetical to the systems engineering culture. So NASA originally in 1962 said, okay, ILC, we'll make your suit, but we'll pair you with a traditional military-industrial contractor, Hamilton Standard, which was a unit of United Aircraft, in order for you to be able to master all the reams of paperwork and systems engineering processes. And this shotgun marriage was not successful at all. And what ended up happening, this is a Hamilton Standard suit that was made in 1966 for what ended up being the pivotal moment for Playtex, which was when this kind of shotgun marriage between Hamilton Standard and ILC had degraded so much by 1966 that even NASA agreed that ILC needed to be fired from the contract. But the suits that Hamilton Standard were making on their own at the time were still inadequate, so NASA had a competition for who would make this last minute. I mean, 1966, it's only a year or two until they actually imagined using this thing, so they were everything was enormously fraught, and there was a 6-week competition was engaged between Hamilton Standard and several other companies. ILC managed to talk its way into that competition because the suit testers and engineers on the ground in Houston knew that the suit was really good, and they wanted it to see it sustaining the process. Now, so ILC managed to talk their way into the competition, but the suit they made was entirely their own. And and here we get to some of the really spectacular failures, because when, for example, one of the competing suits was tested on a mock-up of the lunar landing ladder, the pressure that built up inside the suit was so great that the helmet flew off and actually destroyed the hung ceiling in the room because there was so much pressure inside it. I should, if you're not, haven't thought about it, I don't know why you would have. The fundamental problem of designing a spacesuit is that if you imagine it's a pressurized vessel, it's like a basketball with a much higher pressure inside than on the outside. So it wants to do two things. It wants to be a sphere, not shaped like the human body, and it wants to be very stiff and hard. So this is the really difficult design problem, how you make something that is pressurized like this, that's flexible. So the pressure inside the suit was the thing that threw this helmet off and destroyed the roof of the testing room. And then for another suit that was in this competition, when the test subject was testing it on a mock-up, the same mock-up of the lunar lander, he managed to get out of the lunar lander and get onto the fake moon surface, but the suit's joints at the shoulders expanded so much slowly over time that he couldn't get back into the lunar lander. And so if it had actually been on the moon, he would have been trapped on the surface forever. So by contrast, ILC, of course, had a great suit that worked really well, and so they managed to come back into NASA, but this time as the prime contractor, as the chief engineer themselves, and they had to do an enormous amount of work to not necessarily master this actual process of making the suit, which they could do very well, but to master the process of the paperwork of the systems engineering process. So they hired a whole bunch of people basically to serve as a kind of buffer in their own organization between what they call the hard knocksers, because they'd only graduated from the school of hard knocks, but they really understood how to make the thing, and the people who could give NASA the paperwork it needed to feed this jaw of the systems engineering process. And they never did it very well. There's all kinds of paperwork in the file saying that ILC has yet again failed to produce form 37592. There was an enormous conflict between the systems engineering process and the process of suit making inherently. I'll give you one example. In the traditional systems engineering process, every time a component is changed or given a different physical quality, it gets a new serial number or a new designation in the systems engineering process. But of course, when you're tailoring something to the human body, you're going to make all kinds of changes that don't change the fundamental design of the object, but fit it better to this kind of tailoring instead of design process. And so one of ILC's biggest battles was to be able to size each element of the suit as a small, medium, or a large, instead of giving them all these different serial numbers. And in the end, the practicality of this won the day. They were able to size every part of the suit this way, except for the urinary collection device, which after what was called an incident with the first astronaut fitted, was sized as a large, extra large, and extra, extra large. So, Playtex's next battle came in towards the end of 1968 when several of the hard suit manufacturers managed to get themselves considered as potentially being used in the later Apollo missions with the lunar rover, etc., etc. And to win the day in this competition, NASA, ILC, at this point getting much better itself at the process of image creation, they sent a bunch of paperwork to NASA saying how their suits could meet the increased mobility requirements of these later Apollo missions. But the really winning document was this film in which they filmed a test subject playing that most masculine of games of football on the Dover High School football field and sent it to NASA with the paperwork because convinced them that the suit would be mobile. And yet, interestingly enough, for all of Playtex's success, even so, the popular image and the kind of science fictional image of spaceflight remained controlled by these hard one-piece suit here. This is a photograph taken from the 1970 Expo Osaka American Pavilion, designed by Davis Brody, this big pneumatic structure. And you saw in the course of that exhibit the moon rock, all the different kind of exhibits of Apollo hardware. And then the last vista before you left the exhibit was this kind of half-tone screen of the lunar surface with these hard suits that were never used. placed in front of it, but still somehow projecting better this image of a kind of science fiction future. Which really brings us to some interesting discussions, I think, that are very relevant to our current architectural moment. So this is a DuPont advertisement that shows the 21 layers of the Apollo spacesuit as they were eventually constructed. And one thing I would say here is 21 isn't a magic number. By the end of the Apollo program, the layers had grown to 28. I just chose 21 as the structure of what I'm talking about, because it's slightly easier to deal with as a number than 28. But it's still, what's even more interesting is that each layer of this supposedly incredibly space-age object was actually made of a material that already existed. There were no new materials, no innovations in actual physical fabrication. Rather, what you see is for each operational and functional requirement in the suit, a single material like Teflon or nylon, or most of them made by DuPont, was kind of layered in to add this functionality to a hybrid object. This is very different from the kind of design from first principles that were shown by suits like this one. This is again in Ames AX suit. Here the body is seen from first principles in a kind of very traditional modernist way, and it's not too. I was let's see, intrigued but not necessarily surprised to learn that in fact these suits were themselves designed by a guy named, in part by a guy named William Elkins, who was a student of a protege of Oscar Schlemmer's at the Chicago Bauhaus. So there's a very direct connection between these kinds of geometric visions of the body in space and our own architectural tradition. Instead, of course, the actual spacesuit had this epidermal quality of all these multiple layers of objects. And especially here, when you see this X-ray of the suit and a human hand inside of it from a mobility study, you see what I argue, certainly in the book at greater length, this very intriguing kind of analog between the structure of the body itself inside the suit, multi-layered, complex, robust, and redundant, and the quality of the Playtex suit itself, this epidermal, multiply redundant kind of adapted object instead of the object that's designed from scratch. I think it's particularly interesting too if you look at, we saw the preoccupation of the space race in AD in 1967. If we go to the middle of this past decade, we see a preoccupation in AD, another architectural context, with things that seem like they would be analogous to the spacesuit, with these notions of emergence, morphogenesis, all this kind of biological language finding its way into mostly digital design processes. But here I have a bone to pick, because when you actually look at these ideas of, say, emergence or morphogenesis in their scientific origin, what you find is not objects like this one, in which things are locally optimized to perfect conditions, but rather objects like this one. This is a map of the multiply redundant chemical reactions inside a human cell, where things are never, in fact, designed or optimized parametrically or otherwise for a particular purpose, but rather are assembled over time in an enormously hodgepodge way by an evolutionary process that instead of optimizing things, as we often speak of an evolutionary process doing in architecture these days, in fact, makes things that are inherently suboptimal because they're not designed from scratch. They're made out of other things. Our skeleton is made out of calcium, out of the tendency for vertebrates to have calcium deposits for phosphate storage that eventually turned into a skeleton. Our eardrum is made from bones that migrated up from the reptilian jaw, which means we can't eat anything that's larger than our head because we don't have a multi-jointed jaw, but we can hear. Nature actually has this way of reusing and remaking that's not at all like the kind of parametric, biomorphic kind of fashion, but in fact very unfunctional and multiply redundant. But this hodgepodge, this making of things out of other things, does tend to produce things that have the quality of this diagram and also of the Playtex spacesuit, which is to say that they are not optimally suited to any single purpose, but they're very robust and resilient to all kinds of environmental challenges and changes. This is much less the city as we imagine it. Bring it to the ultimate scale of architecture, the urban scale. This is not the city as we imagine it as a kind of space station utopia perfectly operating according to legible principles, but rather the city as we receive it. This is just a few frames from Ziga Bertov to really see how we reinforce the fact that the actual operation of architecture and urban environments in particular is multiple, redundant, and multi-layered, much in the same way of the spacesuit itself. So this, I'll bring it back here to John F. Kennedy just before I close. This is Kennedy trying on Gemini's suit glove in 1962. And back to this idea of fashioning, because fashioning is a very interesting word in this context. It means not only this notion of presentation. Here we see Kennedy, of course, is the best dressed man in the room, not just because he's wearing a spacesuit glove, but fashioning also means this idea, maybe more MacGyver than haute couture, of making something out of something else, of bringing something to a purpose that it wasn't originally intended for. In the book, I talk about a little bit about Dior's new look as a kind of metaphor for 20th century planning, not least also because the systems engineering was itself called the new look in defense spending by Eisenhower. But this idea of fashioning is particularly interesting in architecture. Here are some, these are the drawings produced by Playtex of the suit process, but they were not drawings produced in the traditional architectural sense. That is to say, they were not drawn before the thing was made. Rather, they were drawn because the thing was made in a way that couldn't actually be understood or accounted for by drawing. It was made in the moment as these women and seamstresses attempted to join together 21 different Russian dolls of fabric, each inside of the other. And it was a process that was not susceptible to a traditional architectural design structure. But it was pointed out to Playtex that drawings were part of that contractual obligation to NASA. So instead of drawing things beforehand, they drew them afterwards. That is to say, in the manner of an anatomist and not of a kind of a proposal. They deconstructed and took apart the objects and drew them as they were as they revealed themselves versus as they were intended to be made. Which brings us to the end here. I'll show you two more images. Well, this is actually one of my favorite images that I uncovered in the course of the book. It's Neil Armstrong, Buzz Aldrin, and Michael Collins leaving the suit-up room, the clean room in which they were put into their suits for the launch pad inside Cape Canaveral's 39A launch complex. And it reveals to me the interesting truth of this object that they're wearing, which is that it was not even so much a buffer between their bodies and the extreme environment of outer space, as it was also very much a buffer between the organizational reality of the military-industrial complex, here with its hung ceilings, perfectly rounded cigarette trays, etc., and the logic of their own bodies, which was highly antithetical at the end of the day to that larger systems engineering logic, and which needed very precisely this kind of buffer, thin, essential, complex buffer between their bodies and this larger environment to survive in that organizational reality as much as it did to survive in the vacuum of the lunar surface. This is my last image. It's the last image of a lot of lectures, but I show it to you here in its original orientation. It was taken from the command module of Apollo 17 when the up of the command module was towards Antarctica, but of course NASA instantly flipped it around to place it into a more traditional frame. But it's more uncanny, I think, in this orientation. And it also shows, and I show the image in particular to point out that we're used to thinking of this image, first of all, as having a kind of inspirational role in the environmental movement. And it did not. in fact. It was a response by NASA to the environmental movement. Stuart Brand stood on the Berkeley campus in 1966 and passed out buttons that said, "Why have not we seen a picture of the whole Earth yet?" This notion, there was this notion that an image of the whole Earth would be so momentous in its emotional impact that it would catalyze the environmental movement that Brand and others wanted to found, and that was the meaning behind the Whole Earth Catalog as a subsequent movement. But when the first Earth Day was held in 1970, the Earth Day flag was a picture of the whole Earth, but it was a painted picture of the whole Earth. And it wasn't until December 1972 when in a kind of misunderstanding of their own purpose, NASA thought that public interest would be sustained throughout the Apollo program, which turned out, of course, not to be the case. Once we'd seen that singular image which Kennedy had conceived, the interest waned enormously, and so NASA tried all these different things. They sent a non-astronaut, a non-military person into space for the first time on Apollo 17. They scheduled the EVAs for East Coast prime time so that they would, but still didn't manage to get them televised. And they even, in a kind of last-ditch effort, agreed to produce an image of the whole Earth, because it actually took quite a bit of doing, because in order for the astronauts to see maximum relief in the lunar surface and to communicate with the Earth, they needed to land on the side of the moon facing us in order to be able to communicate by radio, and then the light needed to be oblique to the surface so they could see the relief in landing, and therefore, by definition, for all the Apollo missions, the Earth and Moon were both half full to occupants of either planet. And so to produce an image of the whole Earth before digital manipulation and stitching, Apollo 17 actually had to go on a experimental trajectory towards the end of its mission to come swing around to the side of the Earth to be able to take this photograph. So it was this very deliberate effort to produce the image. But then the image, for all of the truth of its kind of spaceship Earthness, is also a bit of a lie. First of all, when it was proposed, when Fuller and others kind of conceived of it, proposed this image as an image of the Earth as a spaceship, they conceived of it precisely as a spaceship in the systems engineering mold. If you look at Buckminster Fuller's work towards the end of his life, his attempt to produce what he called a geoscope at Southern Illinois University, it was very, very precise in an attempt to produce a kind of piece of paper big enough that the whole Earth could be conceived of as a systems diagram, as a systems engineered object, which it very much is not. I notice with pleasure that my friend Jim Fleming is speaking tomorrow in this series. He's a historian of climate modification, and climate modification has historically been this attempt to system engineer the Earth, which is a terrible idea for anyone who knows the tendency, the ability of systems engineering to accommodate itself to emergent systems like the body or the scale of the Earth. But then also the image is a lie because we see it, this massive 6 sextillion-ton chunk of rock, and think of it as our home. But our home is actually only a tissue-thin layer of the Earth's surface. It's a very small part of this image, not a very big part of it. And so it's to this thin tissue-like layer, which of course recalls to me the tissue-thin layers of the Apollo spacesuit, and also this idea of, fundamentally, this idea of fashioning and making something out of what we have, that I think is maybe the most essential message for our current historical and architectural moment. That is to say that fashioning, accommodating, adapting can produce these singular, amazing images which have, like the Apollo spacesuit, which have, to my mind, more authority, more promise, and more excitement for the future of design than any singular system-designed, parametrically diagrammed hard surface. So that's the end of my presentation. I don't know if we have time for questions, but thanks all very much.
Yeah, I think we just have time for one question, actually.
Okay.
So,
Question? I don't know if I've blown your minds or bored you silly.
Well, no, I'd like to. This goes back to a question that we started to discuss together in the interview that we did for online. But I guess I'm just fascinated in the idea that something that is usually considered, the realm of, catwalks, and the realm of Zoolander, and the realm of like utter banality and pop culture, actually takes on this kind of literally extraterrestrial importance. It gives human beings the ability to leave the planet. It gives human beings the ability to survive in totally alien and harsh environment. So I guess I'm just kind of curious about that idea that. If you just talk a little bit more about the idea that, we're here we are talking about re-engineering entire planetary systems when maybe in fact what we need is just like a better set of clothes to get through sort of harsher winters and that kind of thing. And that tension between large-scale mega-structural projects and the idea that maybe we just need a better tailor.
Well, I think fashioning, I don't necessarily think that clothing, but by fashioning on the planetary scale, I don't necessarily mean purely clothing, although that is a part of it. And Patagonia, in fact, has defunded all of its winter sports research in favor of summer sports research because of the fact that winter sports are going to die out over the next 50 years as the climate makes snow unpredictable. But that's not what I'm talking about. I'm talking more about the fashioning at the level of making something out of retail, tailoring and adjusting. Not fashion in the kind of H&M disposable sense, but fashioning in a more traditional sense of taking something, making something new out of it that has far greater impact than anything designed from scratch. Fashion is a serious business. It's not undercutting the kind of fabulousness of fashion to say that fashion, I think partly why we see fashion as so kind of comical in the kind of Bruno Zoolander mode is that it's so, there's an undercurrent of seriousness to fashion which has, this is a longer discussion, but it has a lot to do with our own mortality, with our own sense of self and presentation, and the kind of seriousness with which we kind of present ourselves through fashion, something that we're not so comfortable with. And it's the fashion in architecture is all equally a kind of source of both discomfort and interest. We're not comfortable with something that can be both superficial and significant at the same time. So I don't know if that's a clear answer to your question, but I think the kind of I think we need less to be planetary engineers in the tradition of Teller and more to be planetary MacGyvers in the tradition of taking something that already exists and that may be all around us already and fashioning different ways of seeing it and using it that can be both enormously novel and yet grounded in what the evolutionary biologist Stu Kaufman calls adjacent possibility. This is how nature moves, from one adjacent possibility into the other, not designing things from scratch. And this notion of robustness and resilience, which is something that we need to foster enormously, especially in our cities, which will double in size in the current century. The world urbanized population will go from a current population of around 3 or 4 billion people in cities to 7 or 8 billion people in cities by the end of the century. These new urban agglomerations need not to be those kind of utopian space stations, which turn out to be like the space shuttle, very fragile, even though it's a very complex system diagram, but rather a kind of interlinked, robust, and resilient landscape whose ability to deal with change expands with the change and growth that these buildings and environments encounter.
Cool, thank you very much.
Okay.
That's great.
Thanks.